Okay, so we're talking about double integrals. Oh, the next double integral web work, I think it's due at 5 tonight. Is that right? So if you got questions, you can ask me after class or office hours today. But it's due at 5. So, and then for those who have recitation today, you will go. So this was the last example we had last time. And we came up with the region. Remember, so double integrals are what kind of problems? Geometry problems, right? You're going to use the limits of integration to, that describes a region, right? Or if you have a region, you have to be able to write the limits to describe it. And we came up last time with that these limits right here were this kind of pie piece looking thing like this. Let's try that again. Because that's supposed to be a circle. Better? Okay. And so this was y equals 2x, or x equals 1/2 y. And then this was the circle, x squared plus y squared equals 25. And we knew that from looking at this limit of integration where x equaled this square root right here. So that means we're talking about the circle, x squared plus y squared equals 25. Okay, and so this was given as a, what, dx dy means left to right and then bottom to top. So it was given as a type 2, and then we wrote it at the end of class, we wrote it as a type 1, and that meant splitting it up, right? Because the top, so if we want to go to bottom to top first, the top was separated into 2 different curves, right? So we had to split it at, what was that, radical 5? So we had to split it up there and then do it as 2 separate double integrals added together. Okay, so now we want to look at a third way to do this. There's actually a third way to do this, and if you think back to what we learned in Calc 2, do you see another approach or kind of type of approach that might be helpful in something like this, right? We've got this circle, right? We got this circle bounded by these 2 lines here. Yeah, Jacob. Right. So that should look like something would be very efficient in polar coordinates, right? Polar coordinates are based on what 2 quantities? So what 2 variables do we have in polar coordinates? Our independent variable is? Right, angle measure, and that's right. That's our standard trig angle, and it's the same angle we use for the directional derivative, right? It's the angle swept counterclockwise from the positive x-axis. So this is our theta. So the standard trig angle. Angle swept counterclockwise from the positive x-axis, right? And then what's the other variable for polar coordinates? Theta and r, right? Which is distance from the pole, right? Which coincides with the origin in rectangular coordinates, right? So distance from the pole. Okay, and so let's just review our polar coordinates here. So what are the relationships between theta and r, right? So relationship between theta and r. So in terms of like going back and forth between polar and rectangular coordinates. So what does x equal and what does y equal in polar coordinates? You remember this? Yeah, so remember x and y. So if you had any point x and y here, that's your x, that's your y. So the distance from the pole is the hypotenuse of that right triangle. So how can we get r from x and y? Down here. So using the Pythagorean theorem, remember r squared equals x squared plus y squared. And then and then this is our angle theta, right? So this picture right here, it kind of encapsulates the relationship between rectangular coordinates and polar coordinates. And what is x then? So x in terms of r and theta. R cosine theta, right? And y is r sine theta. And again, so r is our distance from the pole, or distance out from what we used to call the origin in rectangular coordinates. And then theta is that angle swept counterclockwise from the positive x-axis. So we're going to have we can do this double integral in polar coordinates, and so this is just a preview here. This is just a preview. We're not going to actually write this one, but so we have a double integral, and then so our fxy, then we'd have to change that function into polar coordinates, meaning get that function fxy in terms of r and theta. Well, we can use these relationships here to do that. So it'd be everywhere there's an x, you would put in r cosine theta, and everywhere there's a y, you put in r sine theta. And then we would be differentiating with respect to r and theta, so we'll just generically call it dA, right? For now, and we're going to show what that is. But so this involves dr and d theta. And we'll show what that is in a minute, okay? So, thinking about how theta varies in this region, right? So theta varies from what to what in this region. So thinking about this kind of the starting angle, what is that? Theta equals 0, right? And along the line y equals 2x. What does theta equal, or how could we get that? What's that? Okay. Is it pi over 3? Yeah. Tangent inverse of 2, yeah. Yeah, so, but more generically, so if this was just kind of it was any, rate of change, we didn't know what that was, or it was something other than 2, then it'd be what? Tangent inverse, right? So tangent inverse. Our tangent gives us our y over x, or sine over cosine. So thetas could be written as tangent inverse, in this case, tangent inverse of 2. And Zach knew that as pi over 3. Okay, so this is just kind of reviewing kind of polar coordinates a little bit, and then thinking about this being could be very conveniently approached in terms of polar coordinates. So let's think about how we think about a double integral in polar coordinates. So here's a in polar coordinates, we have our curves are not y as a function of x, but they're r as a function of theta. So we'll call this F1 and F2, okay? So given some theta, right? So given values of theta, a function would tell you how far you are out from the pole. So this is one such function, the blue one, and then another such function, red. Given a theta, how far are you out from the pole? So here is, then, it's better. And then, accumulating like this. So this is the way we want to think about polar, double integrals and polar. First, accumulating like this. And then, accumulating those like this. So, why don't you talk to the person next to you? What is this showing about how we think about double integrals, right? Okay, so we're accumulating according to what variable first? R comes, we think about accumulating R first. So R would, in this case, R is accumulating from what to what? From what to what? F1 to F2, right? So we're starting from F1 for some arbitrary theta, right? For some arbitrary theta, we're starting at F1. We're going to accumulate for that, keeping theta constant, to F2, and then what? Then once we get kind of that typical accumulation, right, for any angle, then what do we do? Yeah, and then we're going to accumulate all of those, right? Accumulate all of those starting at theta 1 and accumulate theta 2. So the order here is what, R and then theta. R and then theta is our typical order for polar. And that will be the only order for polar, right? So theta first, then R it was not convenient. Okay? So let's summarize that. So here we have it. So I'm showing theta from alpha to beta, and then two functions. So h1 and h2 of theta, kind of similar to what we just said. Okay, and so the first is if we're integrating with respect to r, it's not really top to bottom or left to right anymore, but it's kind of like out away. So starting close to the pole to out away from the pole. So like. So I wrote inside to outside. That's not great, but that's the best I can come up with. But closest to the pole, out away from the pole. It's the way we think about how R changes to accumulate for a given theta. So inside to outside, and then, like I showed in the animation, then theta 1 to theta 2. So starting angle to finishing angle. So this is a different animal than type 1 or type 2. Okay? So starting closest to the pole out to furthest away, and then from starting theta to ending theta, just like I showed you in that animation. So what is dA, right? So what is dA? So dA, what? It's a little chunk of area that you get for a little change in R and a little change in theta. So before we do that, we need to review the area of a sector of a circle. Okay, so if you had a sector of a circle, and so say this is capital R, say this radius here, and let's say this angle is, say, beta. So what is the area of that? What is the area of a sector of a circle? If it's sorry, what I mean to say is, what is this arc length? Not area. What is this? What we need is this arc length right here. So this circular arc length right there. Anybody remember? Yeah, it's the radius times the angle. So arc length is proportional to radius, like how far away you are from it. Okay, and angles are defined by radius. So that arc length, circular arc length is r times beta. Okay, so that we need that little fact here to do this. So we need to figure out what dA is, or a little bit of area. Like dA for rectangular coordinates is either what, dx dy or dy dx. It's easy, right? Because it's a rectangle. It's a rectangle. So you just multiply base times height. That's how you get dA. But this is different now because one of our coordinates is an angle measure, so it's different. Okay, so let's label things here. So this is whatever theta we're at right now. So then what is this angle measure right here? We're talking about trying to figure out a little area element. This would be our d theta. Right? What about this dimension here, from here to here? That's r. And what is this dimension right here? It's a little change in r. So last but not least is, what is that right there then? So this is why we did this, set up this initial little fact here. So this is not just d theta, but that length depends on how far away you are, right? So it's r times d theta, which means that dA is not just dr d theta, right? You also have an r in there, right? So it's r d theta dr. So we still look at that area as like a little rectangular element, but this edge right here is not d theta, because theta is not arc length. So to get the arc length, you need to multiply by how far out you are as well, the radius. Okay, but then normally, like we said, we're going to do which first, radius or angle first? Radius first. So normally we'll write it as r dr d theta. Any questions? Okay, now all this that we're thinking about, and remember though, this is a region in the xy plane, right? So this is going to be for regions that are convenient to use polar coordinates in the xy plane. Our double integral then will involve what? A surface, right? A surface in R3 that we're integrating over this region, just for those ordered pairs in that region, right? So we haven't mentioned anything about that yet. So these are still three-dimensional problems. It's just that we focus in on the region in R2 because that's where we get the limits of integration, right? Limits of integration, just like we saw on the type 1 and type 2. Right, so questions on this derivation of dA. You see why you need r dr d theta, not just dr d theta, okay? Because that length right there depends on how far away you are from the pole. So the closer you are to the pole, the smaller it is. The further away you are, the greater it is. So that's why we need r times d theta for that dimension. Anybody have a question? Okay, so here's some practice. So I want you to define the limits, okay? Define the limits. So our standard polar integral is going to look like this. We're going to have some function of r and theta. That's a surface in R3. And then it's going to be r dr d theta. So this will go from what? Like we said, h1 of theta, h2 of theta. Those are values of r, like inner r to outer r. And then from starting angle to finishing angle. So r first, then theta. So here's a generic polar double integral. We got our dA, we got our surface, and we got our limits of integration. R first, inside to outside, then starting angle to ending angle. So for these, you're coming up with the 4 limits of integration for each one of these. For 1, 2, 3, and 4. And yeah. So I'll take attendance. You can work on those. Okay, Jessica, how about the first one? What'd you say the limits of integration were? Jessica. You can do it on the fly without writing it down. Okay, so radius goes from what to what, right? 0 to 2, right? So like it's gonna start. How about just Jessica? 0 to 2. So along any particular theta, 0 to 2, and then? So now we're asking, where's our starting angle and what's our ending angle? It's from 0 to, so question is, what angle is that right there? Close. That's actually 5 pi over 4. 4 pi over 3 is a little bit further. Okay, so that first one would be from 0 to 2 and 0 to 5 pi over 4. Does it make sense? Okay, how about this next one? Tasha, did you get it? 1 to 3, right? So r starts at 1 and ends at 3, that's right. Pi halves, our starting angle is pi halves to pi. Does it make sense? Camille, how'd this next one go? 0 to 2, 0 to 2, right? Start with 0 to 2. Seven pi fourths. So from 0 to 2, and then starting angle at pi, finishing angle 7 pi over 4. Last one. Michael, did you get it? 2 to 3, so we start at 2, out to 3, right? Good. So the starting out here is negative pi fourths, 2, 3 pi over 4. Or you could have said 7 pi over 4 to 8, 9, 10, 11 pi over 4. Is that right? Yeah. So you could have said 7 pi over 4 to 11 pi over 4. But normally we work in the angles, say, like between negative 2 pi and positive 2 pi. Normally we stay 0 to 2 pi whenever possible. And then if it's starting something like this, we might use some negative. So normally we stay less than 2 pi in terms of angles. Okay, questions on those? Do they make sense? Coming up with these regions. Anybody have a question? All right, so let's look at an actual problem now. Yeah, please.
Did you split them up into 2 integrals, or is that just like
You would never do that if you didn't need to.
okay?
I mean, so yeah, so you can split this up into 100 integrals, right? So, but you only split it up into multiple integrals like when there's a necessity for it. So these would all be done with one. But yeah, we will see situations where you will split it up. Yeah, please. Yeah. Yeah, so how does this work? So this everything's multiplied together here, right? It's all multiplied together. So what's going to happen to that r? What's that? It's not a constant. It's r. It's a variable, right? R is one of our variable quantities here. Like all these r's are changing. 0 to 2, 1 to 3, 0 to 2, 2 to 3. What's that? Yeah, well, yeah. So this is going to be a function that this is going to be an expression that has r's and thetas in it, right? It's going to be an expression that has r's and thetas in it, and then we're multiplying everything together. So what happens to the r? It just so it came from the dA, right? It came to the table, came to the party with the dA, but then it leaves the party with the function, right? So it's gonna multiply into the function there, and then when you do your integration, you're going to integrate there. Okay, we'll see that. Any questions? Let's do an example. So here's what I want to do. I want to first want to sketch the region in the xy plane. Change the order to dx dy. And let's hold off on solving it. Let's make sure we have time. So let's just pause. So just we'll wait. Hold off on solving. I want to get through. No, we have time. So you're going to change the order to dx dy and solve it. And then we're going to change the integral to polar coordinates and solve it. How are we going to determine the limits from the polar coordinates? What's that going to be a matter of looking at? What's that? And how will we figure those out? From what? Okay, so in terms of getting the limits of integration, though, where are the new limits of integration going to come from for the polar double integral? Picture, right? The picture. So again, the new limits of integration. But yes, this will come from our formulas. So changing the function is kind of what you were talking about, changing it into r and theta. But changing the limits of integration comes from the picture, just like we talked about, right? In terms of these are geometry problems. You get your region, and then you rewrite your new limits based on the region. Okay, so you've got your task here. 1, 2, and 3. So sketch the region in the xy plane, change the order to dx dy, solve it out, then change the integral to polar and solve it. Go. I got 15 minutes. What's the right side? So what is this thing here? What is that? Okay. Well, that is solved for y, right? That is y. Yeah. So just looking at that, what is this thing? Right? What is this thing? Better? Yeah. What circle is it? What circle is it? Usually when we write circles with square roots, though, right? How do we usually write the equation of a circle? So we're using the square roots because we have to solve for the variables, but normally it's just. So what circle is that? X squared plus equals. So now we're going to go from left to right first. So left is. So going to be x equals, was it? Right? 2, 0, right? So those are left to right. And then from, we're going to accumulate all those typical strips from the bottom to the top, which is from -4 to 4. And then this doesn't change, right? So now it's okay, how'd we do on rewriting it? So the question is, can we do that? Negative square root of 16 minus y squared, is that right? All right, now polar. So in polar, so again, we just practiced, so we're going to write the limits. So what are the limits? What variable comes first? What's that? R. So R goes from? Zero to what? R goes from inside to out, right? Yeah, this is not going to have negative R, right? So it's going to be from 0 to 4. And then theta from pi over 2 to 3 pi over 2, right? It's just like now, so writing these limits is just like those practice problems I gave you. So pi over 2, 3 pi over 2. Okay, now we have to rewrite this in terms of the x over squared, x over y squared, in terms of polar coordinates. What is x? So we got r cosine theta, right? R cosine theta over, so before we plug in r cosine theta and r sine theta, let's think about it here, square root of x squared plus y squared. That's just r, right? That's the hypotenuse of the triangle with x and y as the flanks. Because r squared equals x squared plus y squared for all right triangles. Square root is going to be r, and then our dy dx becomes dr d theta? R dr d theta, and what happens to this r then? Well, in this case, it cancels, but normally, so it multiplies in with our function, right? It multiplies in with our function. In this case, it cancels. So here we go. Antiderivative of r cosine theta with respect to r. Yep, so we're going to have, this would be from pi over 2 to 3 pi over 2 of 1/2 r squared cosine theta from 0 to 4. So that's going to be, so in this case, when we plug in 0, we do get 0. So it's going to be 16, it's going to be 8 cosine theta. Is that right? Here. So it's going to be the integral of pi over 2 to 3 pi over 2. 8 cosine theta. Antiderivative of cosine theta is? Sine theta, so 8 sine theta from pi over 2 to 3 pi over 2. Sine of 3 pi over 2 is? The y coordinate at the bottom of the unit circle, -1, so we got -8. It's going to be minus sine of pi over 2. Minus 16. Okay, what's the meaning of that minus 16? What does that mean? Weren't we supposed to get the area of this half circle? Is that what we were supposed to get? No? What did double integrals give? Net volume, right? So what does this tell us? If we have negative 16, what's that? Yeah, so minus positive 8, right? So negative 8 minus 8. Yeah, yeah. So negative 16, what's going on here? Yeah. Right. So, so even looking at the, so now if we think about that surface. So this is, think about this surface. We're in the negative x territory, right? So what can you say about that function when x is negative? Is it always negative? You see, it's always negative. That's positive. That's always positive. And here we are to the left of the y-axis. So x is always negative. So we can say definitively this negative 16 is what? It's not a difference of volumes, right? Yeah, so the volume is, so there is a volume of 16, and it's all below the xy plane over there. Do you see that? So this is, and that's why we're getting negative 16, because it's a volume of 16 below the xy plane. Okay, and so then the other task was to solve this. So just looking at that, so this is doable. Look, because it's a chain rule, right? See, this is a chain rule derivative, because the derivative of this x squared is this x right here. So you can think about that being the result of chain rule and kind of undo the chain rule if you were in my 271 class, or use substitution. But it's a lot more work than this. That's the point. Because this is so nicely, oriented for polar coordinates, it makes the solving a lot easier, right? That was a pretty easy double integral. This is more involved. This is doable, but a lot more work. But you should get the same thing. You get the exact same thing, negative 16, if you did the work. Okay, lots of good things in this example. Any questions?